Foundations of amateur radio. Amateur radio as a hobby is one of those activities that covers a wide range of pursuits. A fellow amateur once referred to it as 1,000 hobbies in one. I like that as a description, but it really doesn't cover how wide and extensive this hobby really is. You've heard me talk about radios and on-air activity, about contesting, about outdoor activities, about electronics and antennas, about the grey line, and about decibels. Today I'm going to talk about the sun. Using a handheld radio, you're often using higher frequencies, 2 meters or 144 megahertz or higher. These radio waves mostly travel along line of sight. If you look at the lower frequencies, called HF, 28 megahertz, 21 megahertz or lower, then those radio waves also travel line of sight, but they also travel up into the ionosphere surrounding the Earth. If you manage to hit the angle just right, then some of those will reflect off the ionosphere back to Earth. It's a lot like skipping a stone on a pond. If you get it right, you might make it skip several bounces. If you get it wrong, it'll go plop and vanish. The same is true for these frequencies. One of the things that makes the ionosphere reflective to radio waves of a certain frequency is the level of ionization in this area around the globe. Typically, the ionosphere is somewhere between 50 kilometers and 1,000 kilometers above you right now. At different heights, the ionosphere reacts differently, and the sun shining on it will alter the properties as the day unfolds. This is why when night turns into day and day turns into night, special things start happening along the border between day and night, the so-called grey line, where it's not quite day and it's not quite night. One way of looking at this is that the ionosphere heats up during the day. Now, heat is an interesting thing. The sun shining on your skin is experienced as heat, but what's actually happening is that the radiation from the sun is exciting the electrons on your skin, and you experience that as heat. As a matter of interest, the sun generates about 650 watts per square meter in the middle of the day, coming through the atmosphere. That's about 650 joules of energy per second per square meter. Lots of excitement. At the outside of the Earth, there's about 1,300 watts per square meter. The difference, 650 watts, is absorbed by the atmosphere. So the equivalent of the heat you feel on your skin is also heating up the atmosphere. Now, this heat is really energy that's exciting electrons and thus also exciting the ionosphere. At the simplest level, this is making the ionosphere more reflective to radio waves. I'm deliberately simplifying this because I don't want to get bogged down into how precisely, because my point is about the sun and more specifically about sunspots. There, I said it, sunspots. What are they and what do they have to do with anything? Well, a sunspot is a cool place on the sun. When I say cool, it's about half as warm at a sunspot than the area around it. Only 3,000 degrees Celsius instead of 6,000 degrees. Sunspots appear in pairs on opposite sides of the sun and represent a point on the sun where an intense magnetic field comes through the sun. You can think of it as a huge racetrack through the sun that accelerates particles from the sun into space. These particles represent energy, and if they happen to hit the Earth, they add a whole lot of extra energy to the ionosphere, making it much more reflective. The more sunspots, the more energy, the more excitement of the ionosphere, the more reflection, the better radio communications. Sunspots generally appear in groups, and the density of these groups varies over time. To get a uniform sense of how much energy is around, scientists came up with a sunspot number. It's indicative of how much energy there is, not an actual count of the number of dots on the sun, since some spots are large and others are relatively small. The increase and decrease of solar activity repeats over time. Using carbon dating, we can get well over 11,000 years of solar activity, which has led us to say that we have a solar cycle that lasts about 22 years. Of course, that isn't exact since this is nature, but it gives us a simple way of better understanding a very complex topic. The final bit of information you need is that when the amount of solar activity has peaked, we have hit solar maximum, and when it's hit the bottom, we've hit solar minimum. Since you cannot see those while you're in the middle of it, you can only really look back in time to determine what the exact point in time was that this occurred. Another way to detect that we've hit a minimum is that the magnetic pole of a sunspot reverses. As I said, they come in pairs. One is the north pole of the magnetic field, the other is the south pole. When these reverse, that's an indication that we're starting the next solar cycle. All that being said, it means that sunspot activity is strongly related to your ability to use HF over long distances, and if you're a QRP operator like me, using 5 watts to get around the globe, then you really want to know when the sun is helping you and when it's taken its bat and ball and gone home. I'm not going to go into solar flares, coronal mass ejections and the solar wind, since that's a whole new topic to cover for another day. Suffice to say that too much of a good thing is harmful to radio communications. The sun and solar cycle is an amazing topic that is just another aspect of our wonderful hobby of amateur radio. I'm Ono, Victor Kilo 6 Foxtrot Lima Alpha Bravo.